Okay, now that's lecture 2 on Bayesian methods. So let me continue what I started yesterday, and let me just bring that. Where is it? Okay. So okay, when up to this point, at least in probability theory, we had, say, distribution. For example, if we had exponential, say, lambda, then lambda was either given to us or we could find it given some information, but it was a fixed number. So lambda fixed. But what if lambda is not fixed? Lambda is a random variable. Then what? How can we find the probabilities given lambda as a random variable? Well, if either we are given lambda or we have to find it somehow. Okay, so let me start with a simple example, and so you understand what this thing means. So this example is so example number 1, and I will use this another in some other context too. This is example number 1. So a coin is tossed just once. Okay. So a coin is tossed just once. Now a coin is either a head or a tail, right? So remember we modeled this using Bernoulli random variable or Bernoulli distribution. So we would say that x takes h or t, and we would say that p of x being h, for example, is some p, say, and then x would be Bernoulli t. Okay. Now, what if this p is not a fixed number, but a fixed by a number which is not fixed? I mean a random number. So we need a distribution for this. So we have x is Bernoulli p, and p itself has a distribution. So what is the distribution? It's given here. Let me so it is this. So distribution means I should give you the probability. The probability that this p is 3/4 is 0.2. The probability that this p is what's the next one I have here? 2/3 is 0.25, and the last one is the probability that p is I think it is 5/6. 5/6 is 0.55. Okay. So this is distribution, right? So what are the values that p can take? These are the values, and these are the probabilities. So this, I can write a PMF for this thing. So we say that PMF will be something like this. F of t will be 0.2 if t is 3/4, is 0.25 if t is 2/3, and is 0.55 if t is 5/6. Okay, and we want to find p of x is h, and these are probabilities that x is h. Okay, that P is probability that x is h. That's okay. So let's use the law of total probability. So this is P of x equals h, given that small p is 3/4 times probability that small p is 3/4 plus probability that x is h, given that small p is 2/3 times p of small p is 2/3, and the last one is plus probability that x is h, given that small p is 5/6, p of small p is 5/6. Okay, so that is law of total probability, and this h depends on p. With different p, we have different probability. Okay, well, this is just Bernoulli. So, what do I have here? I have, well, let me see if I can write with another color here. So, what is this? Remember, this p is probability that x is h. So, this is 3/4. And this from here, 0.2. This one is 2/3 by, just it's right here, times 0.25. And the last one is, this is 5/6 times 0.55. Okay? So, that's it, and I will get, I have the result here, 31/4. So that is the probability that we get heads. Now, if it were just 3/4, you would just get 3/4. But it was just this one, but we have a distribution. That's the meaning of distribution, right? Remember, distribution was giving probabilities for everything that this random variable takes. So that P as a random variable takes those 3 values, and the probability of P taking any of those values is given. So that is what I mean by distribution of P. So not just X has a distribution, this parameter also has a distribution. And using the law of total probability, we can find probability of X being something. So, so this law of total probability has amazing applications here. Now, let me see if there is. Okay, now, let's say a coin is tossed once again. So this is example 2. Coin is tossed once. And we basically have no idea what that P is. Nothing is given to us. We can choose something. We can just come up with some, say, a distribution and say, okay, this is what I think it is, and find it. But when you have no idea, you will see in the Bayesian stats that I will just take a look at that at the end of this lecture, or maybe next lecture, that when you have no idea, just to pick a distribution, which basically means no idea. Well, I shouldn't say that, but anyway, a uniform distribution, okay? So you say that P can be just any number between 0 and 1. Okay, what's that? That's just uniform distribution. Okay, so let's say that X is Bernoulli P, and let's say that this P has uniform distribution and 0 and 1, right? Because P is probability, so it is between 0 and 1. And So it is a nice choice. So we have no idea. Now let's see how we can find probability using this. Probability that x is h. So p of x is h. Well, you say, okay, this is saying, okay, let me write something here. Then p of x is h given this. Probability that p is what? But when we are talking about a continuous distribution, remember, we cannot talk about p of small p being, say, 0.5. This is 0. But we can talk about p of small p being between, say, 0.5 and 0.6, right? So we can talk about probability of this random variable between two numbers. So let's do this. I need two numbers, but I write this. I say, okay, what if p is bigger than, say, some t, less than equal t plus dt? Probability that p is between t and t plus dt. So I just move, this uniform distribution has this PDF, right? 0, 1. So this is like t, and t plus dt, and in fact dt is so small, but I have exaggerated here. So that is t plus dt. Okay. Now, what is going on here? Well, first of all, when I talk about this, this is like probability in one small area, right? Remember from Calc 2 or Calc 1, I can remember which one. This thing is called differential, right? So, in fact, I'm finding differential of p, not p itself. This is differential of p, because I'm just finding it in some small interval, dt, which goes to 0. So that's, in fact, differential of p. Now, in this region, well, I have a uniform distribution here, but even if I did not have uniform distribution, in this region, p is the value at t, okay? P is the value of the PDF at t. Okay, so, because this is just, so I can just say that this is 1. In fact, it is 1 for any, this p is in fact, sorry, t, what I'm saying, this is t. Right? So that is t. Okay, the value of p here, that's p. What is this one? Because p between t and t plus dt is almost t, right? This is probability that t is between this and this. This is in fact the, you see, the PDF, in fact, or even in PMF, PDF is what? Probability density function. So density is density. So that PDF gives the density of this x-axis from 0 to 1. It gives density of this from 0 to 1. But this density is continuous, right? So if so probability means that the mass of this thing, this part of the x-axis, using this density, right? Well, what is this? If I say that this is the density of something, or density of x-axis from 0 to 1, then if I want to find mass of this area, this part of the x-axis, in fact, that is this density, this integral, right? So since t and t plus dt are so small, it becomes this area. So this area basically gives me this density. Obviously, the mass of this thing. So what is it? It is the value at this point times dt. So it is the value at this point 1 times dt. This is mass of that portion of the x-axis, given that the x-axis has density, which is density of this p. Remember, density of p is how I should write it, the density of this variable. Yeah, remember, density of this thing, the PDF of this thing is what? Is 1. Simply, it is 1. The PDF is f of t is 1 when t is between 0 and 1. And it is 0 elsewhere. So, if I had something else, then if I had, say, t squared, for example, it would be t squared times dt. In this case, it is 1 times dt. So, dp, the product that I'm finding, its differential is t dt. So the probability itself is integral from the t goes from 0 to 1, depending on the range and the domain of t dt, which is in fact 1/2 t squared from 0 to 1, which is 1/2. But 1/2 in fact is the average of t, average of p. Which you can see, that is t dt. That's t times 1 times dt. So that is in fact expected value of this p. This is expected value of this p. E of this p. So, yeah, we got 1/2. And it makes sense. We don't know anything, and so what do you expect to get? What you expect is basically 1/2 in this case, because we are just doing it one time. Now, it's not like this all the time or for other distributions, but anyway, so in this case, we had this situation. So, if x was something else, then this would be, well, let me erase this area here. If x had some other distribution, then this would be x equals h. P is close to t, so that is t. And that would be if I had, for example, this distribution instead of that, for, say, right, something like this. Okay, so that was like f of t, some distribution for p. Then that's for p. Then the mass of this, that is probability, the density function. So it is density of the x-axis from here to here. So density of the x-axis at any point is the number on the y-axis. So this is density, and the density times dt will give me, or density at this point is ft. So this would be ft dt. So in that case, p of x being h, if would be something like this: p of x being h given t, ft dt. Okay, so depending on where it goes from, well, in this case it is 0 to 1, say, for example, because if it is Bernoulli or binomial, that p is a probability, so it's between 0 and 1. But anyway, that is, again, I will get the expected value, right? That I will get the expected value of p, but that's because it's Bernoulli. Bernoulli gives me expected value. If I had something else, then I would get something else. So if I had like binomial, this would be another expression. For Bernoulli, this is simply t, whatever that t is. So there, I mean, whatever that distribution of p is, I will get t ft dt. That's the expected value of that p. Okay, so that is the continuous case. I will give you formulas. In fact, they are in the notes that I will post sometime, maybe today, tonight, in fact. Okay, so let me yeah, then after this, I have in fact, as I said, I have given this as a theorem or a proposition here. So I have said that this is like a theorem or proposition, and I said discrete continuous case. That is when x has some distribution with theta as parameter and x with PMF f of say x say, and theta as distribution has some distribution with PDF some g theta. Let me see what I have used here, g theta. G theta. Okay, so yeah, dp in this case, so I want to find p of x is say a, so I have to find d of p equals a. So I said, okay, this is p of x being a, given that this theta is between t and t plus dt, and the probability that theta is between t and dt. Okay, so this dt is so small when I integrate this thing, so this is basically almost equal to p of x equals a given t. So this is this, and that one I showed you in the picture. Well, I don't know what the theta goes from to, so maybe theta goes from theta low to theta high, or it can go to infinity. Depends. And so that is in fact that g theta. This is g theta. G theta is density of this. Okay, so it's like this is a rod here, and this rod has some density, and density is smaller here, smaller, and then it gets denser as it gets to the end, and so in the middle it's like denser, and then gets again not that dense at the end, right? So if I want to find say mass of this x-axis from t to t plus dt, when I have the density of the x-axis, this will be the value of density at this endpoint, gt times dt. In fact, this area is the mass of this thing, right? That area is mass of this thing. In fact, integral, when you find integral f to dt, it's like saying that this it has like mass of something, right? So, anyway, so this will be the mass of that small area, which is gt dt. Okay, so that is dp. So p of x equals a will be integral from theta L, theta u, p of x equals a given t. Now, where does this go? This goes here. This fx has t inside. So, in fact, I can, but we will see that when it comes to the stats, in fact, we have like a joint distribution of x and theta. Okay, but anyway, this definitely has some theta. You know, just remember, like if this fx is, for example, for exponential function, exponential distribution, this would be e to power lambda t, something like that, right? So this lambda is like that theta. So if x is exponential lambda, you see that lambda is part of this formula. So that that parameter is always part of the formula. So here also we have, so this will be this fx with t as parameter. Okay, and then gt, dt. So if x is discrete and theta is continuous, that's what we have. If both of them are discrete, that's basically the what was that? That formula, the total probability formula. So, okay, now this is like that formula, except the distribution of the second one when we say p of x given y, x is discrete and y is continuous. So this is like that one, and you can see that y is that one is sigma summation. This is in fact integral, so that summation becomes integral here. Okay. Now what happens to the case when we have discrete continuous, we have the continuous continuous? It's okay. I mean, I'm not going to give you an example of continuous continuous, but it's good to know the formula when we have continuous continuous. And I just write down, so x has some distribution with theta, and fx is its PDF. In this case, we don't have PMF, PDF. And theta is some distribution with gx, g theta as PDF. Okay. So it's similar to that, except I'm not going to prove that it's in that form, in those notes, so it will be from theta L, if this one goes from theta L to theta U. And this distribution might be from negative infinity to infinity, depending on what we are looking for. So if I'm looking for x bigger than a less than b, for example, then this will be a and b, right? And then this should be over every possible theta, like the law of total probability, which is over every possible theta. And I have f of x given theta, so I put this theta here, g theta, d theta. Okay, so that will be the formula for probability when the theta has distribution, some distribution with PDF g theta. Okay, so let's see how we can use this thing and do some stats. Say, okay. Well, this last one was in fact the most general form of that law of total probability. Now, let's look at Bayesian stats, some glimpse, as I said, on Bayesian stats. Well, it is some long story, but I'm just trying to give you some taste of what is this thing. So what is it? Remember in the stats that we had, that frequentist statistics that we discussed for some time, well, you either choose some distribution or you are forced to choose some distribution, and the distribution has some one or more than one parameters, like normal distribution has 2, for example, exponential has 1, and so on. And then you could say something about the distribution of that parameter. You could find, say, confidence interval. You would say, okay, this theta, or let's say the average value of that. You could say something about the average value of the distribution of theta. And you could say that this, with some confidence, lies within some intervals. Something like that. We discussed that a long time ago. So, but this is kind of similar to that. First we choose some distribution for what we are studying, which has some 1, 2, or whatever parameters, if it's more than one. Then we assume some distribution for the parameter, and that distribution for the parameter is called prior distribution. Then we do some experiment. We gather data, and using that data, we correct our guess. So we make corrections on our guess, and we find a distribution for theta based on the data, and that is called posterior distribution based on data. Now, for this, we assume that x is like what we are studying, so and theta is the parameter. Let's just say we have 1, and we assume that x they have joint distribution. With PDF, let me see what notation I have used there. Yeah, g of x and theta. So this is in fact a random variable, not that small theta. And we define, say, marginal distributions. Marginal distribution. The marginal distributions I chose, let's see, what did I choose? The one for theta is usually it's called pi theta, and that is in fact integral of gx theta, and this is over x. Now I don't know what x goes from, say, a to b, whatever that is, depending on the domain of x. So I think I chose in this definition I chose some domain for both x and theta. Then h x that is marginal for x, and you can guess this is over x. Okay, so when you integrate over x, remember when you do double integration, say in the inside, for example, you take you integrate the inside with respect to x, then the x goes away, and the other variable remains. So when you do integration here, theta stays. Theta is like constant here. So this whole thing becomes a function of theta. And that function is in fact what we call a prior. Okay. And this one, as you can guess, is from C to D, for example, and then that's again gx theta. This time it is integral over d theta. So these are marginal distributions, and we have conditional distributions. So what is conditional? These are in fact, well, what notation I used? So I used f of x given theta, and that is in fact gx theta over pi theta. And the other one is what notation? Xc theta given x, which is again g x theta over hx. Okay. So look. So this is the distribution I start with. This I assume that. I assume that this one I know. And this is the one that I end up with. So this is what we call a prior, and this is posterior. And you can see that this one is a function of theta in fact, because x is given. So this x is what you do when you do some experiment. Say, I will give you examples and you will see how it works. But anyway, this x goes away because that's like a number. Just put a number over there. Say x equals 5, 10, whatever. So this will be just a function of theta, and that is the posterior. So this is your belief. Like when I said we absolutely don't know what P is for that coin, and so it's in fact saying that I believe that it can be anything between 0 and 1. That's why my belief was that pi theta is uniform distribution on 0, 1. has uniform distribution on 0, 1. Okay, so you start with your belief, and then you do some experiment or experiments and come up with a distribution for data again. That is based on your data. So this is like, this is in fact the Bayesian method. Now, you can guess that these two, for example, when I have discrete distribution, that will be just sigma. Okay? So instead of integral, we have sigma. This one is sigma over x, this one is sigma over theta. But anyway, this one is given to us. We don't have to do too much here. Now, so the formula is this. Putting this together, we have to find, so g of x and theta was, on one hand, it was xc, theta given x, hx. On the other hand, it was f of x given theta, pi theta. So xc of theta given x is basically this. F of x given theta, pi theta over hx. So this is in fact, some people just call it like Bayes' formula in this situation. And you can see this is in fact like, recall that probability that x given y, for example, or a given b, not x given y. It's events a given b, remember that? Was b given a, say, was p of a b, p of a divided by p of b side. This is b divided by p of a. Just look. This is this, remember? And just compare. So, for distributions and PDFs or PMFs, we have something similar to this Bayesian formula or Bayes' formula in probability. So that's why it's called like Bayes' formula. Okay, now let's see how this thing works. In fact, the rest of that is basically finding this. So you make a choice for data, and then you find posterior theta. So, okay. So now let's go back to that coin example. Example was so the coin again, unfair coin. So unfair coin, and we started with unfair coin. What was it I started with? Okay, so pi theta. So unfair coin was x was Bernoulli theta and pi theta. Now in this situation I know pi theta, and pi theta was 0.2. When theta was 3/4, it was 0.25. When theta is what is the second one? 2/3. Yeah. 2/3 here and 0.55. When theta is 5/6. That's pi theta, right? So, what is f of x given theta? F of x given theta is probability of x is h given theta, right? So that is theta so let me see. Yeah, this is in fact theta to power x 1 minus theta to power 1 minus x, right? depending on x being 0 or 1. So x being 1, that is h, x being 0, that is t, right? So x can be 1 or 0. I use 1 or 0 here. It's customary to use 1 and 0, 1 for h and 0 for t. And so that is this thing. So look, if I have x is 1, this is 0, and this is theta. If x is 0, this is not 0. This is 1, or this is 0, and this is 1 minus theta, which makes sense. So depending on this thing, so let's not write h here, let's write x equals x. Not h. Okay, so that is the f. So what happens to xc? Xc of theta given x equals x will be, what was that? F of x theta, remember? Given theta, pi theta over hx. Okay. We found hx for x equals h, remember? For heads. That was 31 over 40. So we found hx, remember? We found hx, that was p of x given h, when x is h. So this is the formula. Let me, how can I, so do I have space somewhere? I think there's this thing. Okay. So first let's find this when x is h. So xc of theta given x is h or 1 is f of x theta, which is this, theta x times 1 minus theta, 1 minus x, and we found hx to be 31 over 40, right? Okay, so that's the times pi theta. Okay. So now we have to find this for different thetas, right? Because pi theta is discrete. So this will be, if theta is 3/4, just plug in, and in this case x is 1. So I found 6 over 31. When theta is, what was the second one, 2/3? It is 20 over 93. Well, I'm not really, these are quite well. You can check my calculations, and then theta was, the third one was 5/6. Theta is 5 over 6, and that gives me 55 over 93. But if you add them, you will get 1. So in this situation, that is the distribution. So xc theta when x is 1 was, when x is 1, that was like 40 over 31 times theta pi theta, right? Theta, pi theta, and pi theta has a value, so theta just is 3 values, and if theta is anything else, this will be 0. So for anything else, it is 0. So I can write it down in this form. So the distribution is this. And then I can ask this question. What is the probability that it comes up heads the second time? So I toss it and comes heads. So that's the experiment. So one time it was heads. Based on that, I changed probabilities. Remember, this was 0.2, 0.25, 0.55. Now look, this one at least 0.55, that was 55 over 100. Now it is 55 over 93. So this is higher. It's telling me that this 5 over 6 is more probable than, say, this one or this one. This is least, let me see. This is least probable because that's 3 times it. That's 18 over 93, 20 over 93, 55 over 93. And is that 55? I'm not sure. Doesn't look, well, I think so. I'm not sure. Maybe I made a mistake because they should add up to 1. Anyway, I will check my calculations in the notes. Maybe something is wrong. Anyway, so I changed from 0.2, 0.3, and 0.25 and 0.55. It changed to something else. I think that something is wrong. It can't be 6 to it. One of them, well, just check. I'm not sure which one. I will post the correct one for you. Okay, so what is the probability that the second time that I toss the coin, it will be heads? Okay, so the question, second question is second time. Now for the second time, X is again Bernoulli, but this time theta has distribution which is with PDF, XC, which is in fact PMF, not PDF, PMF, XC given X, right? So for this one now I used those 3. Let me, I'm not sure, 20. Why is it third one? Can't. But the third one is correct, but one of them is not correct. 50, that's 2. I'm not sure what is going on, but I will check that. So anyway, so that P of X equals, say, H, given this data, given this data, so this will be, again, like that one is P of X is H, given theta is 3/4, P of theta is 3/4, plus P of X is H, given theta is 2/3, P of theta is 2/3, and the last one plus P of X is H, given theta is 5/6, and times probably that theta is 5/6. So using the law of total probability, and this time I will use these numbers, in fact, which I probably have to change them and find the probability. And I will see, did I use the correct ones here? Doesn't seem to. Well, I have 1.28, but I will check. Well, when I post this, I will make corrections. And anyway, so that is what happens. So after first time, one experiment, we changed the distribution. That is a different distribution. Using that distribution, you can make prediction for the second time. Now, if you do it 2 times, 3 times, 4 times, then you can change it again and again and again. And say if you do it 100 times, then that is fantastic, because in 100 times you have a nice idea of what the distribution is. Now, as I said at the beginning, that was my belief, or the person who has given this problem, which I wrote it just at random. I just chose some numbers. So that was like my belief, that this, whatever I had here, 0.2 and 0.25 and 0.55 was my distribution. So that was my belief, but based on experiment, I changed my belief, and when I do more and more experiment, I change it. Now, I'm not sure if you followed, like about 4 years ago on a presidential, say, election. This site 538 was changing everything every day. They use Bayesian method. So based on data from the previous day or based on polls, for example, in the previous week, for example, they would change everything and they would give a new prediction or new numbers. So that's how it works. Now, this year we are close to that, so you can just check 538.com and see how it works, and you can see, you will see that like maybe it's like every week. I think they do some of them every day these days. But anyway, so that's how what happens. So they start with the prediction the first day. They might have even predictions right now, and then they continue and they make corrections to the prediction. I mean, to this parameter of whatever that is, whatever distribution they have. Okay, so now this is the other case when it is a binomial. So let me give you this binomial case, which is in fact more interesting than just one time. That's what I said. You do it more than one time. Yeah, let me see about that. Yeah, I just give this example. It's over 15 minutes, but that's okay. So this is in fact saying that the coin is unfair and toss it 15 times, and we have 10 heads. Okay, so let's find Xc. Theta given X, and that is theta given X is 10, right? Because I now have some number here. Is f of x is 10 given theta I theta over h x is 10, right? But what is x then? 15. X is binomial 15 theta. So